But today I want to talk about quantum mechanics. And it's one of those chapters that is, to say the least, a challenge. So glad you're here. Once again, if you want to ask me questions, you can click the Q&A button and drop a question there, or you can use the chat menu. Usually you have to go to the three dots there on the end of your menu bar, click on that and open up the chat, and then you can interact that way. So let me get my screen video turned off, and we'll get started with our presentation today. So like I said, we're talking about quantum mechanics today. And here I'm talking about both the history and the doing electronic configurations. Once again, if you're not familiar with me, my name is Jeff Anderton. I'm the owner and founder of Teaching High School Chem. And I grew up in Marietta, Georgia, which is a suburb of Atlanta. So I grew up in probably the least southern city. I have a degree in chemical engineering from Georgia Tech, and then I have my secondary science education from Kennesaw State with a focus on teaching chemistry. And I've been teaching chemistry since 2001. And so it's been a big part of my life for a long, long time. Ever since I took chemistry in high school, I just fell in love with it. And it's just one of those things I've always enjoyed. And then for the last year, I've been pouring my energy into helping you. It is the thing that gets me excited. That's why I'm doing the summer workshop series. It's why I have my products that I have. I get energized by helping you. Just like hopefully you get energized by helping your students, I get energized by helping you. All right, so with quantum mechanics, hard's not the right word here. Weird's a better word. Usually it's confusing stuff. Quantum mechanics is that stuff where my students' brains just want to explode. Like, the whole, hip thing, mind blown, really does apply to quantum mechanics. It'll mess with your head. And so, things like wave particle duality. Oh, by the way, that's both a wave and a particle at the same time. Yeah, sure. Or uncertainty. Hey, we're not really sure where this thing is. Or Schrodinger improbability. Schrodinger's cat. If you're familiar with that idea of, is the cat dead or alive? Well, it's both until you open the box and you're just kind of like, huh? That's stupid. Yes. And yet that's the basis of how we view atoms, and it's a huge deal these days that a lot of things in the science world are viewed through a quantum lens, and how it affects things, quantum computing and all that. So for those reasons, it's an important topic that the kids need to be exposed to. Just this idea of quantum mechanics. And then we get into actually doing electron configurations, and you got the three rules that govern everything, but they're pretty abstract. And we've got to have some way of trying to make it okay for kids to struggle with this a little bit. And that's my big thing. I don't have this listed as strategy number one, but this is my strategy number one. You got to give students permission to be confused. I kid you not. When I start doing this, I say this in class. I say, all right, guys, give me 3 days. If you're confused at the end of day one, you're fine. If you're confused at the end of day two, you're still okay. If you get to the end of day three and you're still not getting it, then we need to talk. But just give me 3 days. And then I'm patient with them along that process too, of just like, this is weird, and it takes some practice, and it takes some getting used to, and it's abstract, and it's confusing, and it's hard for kids to wrap their minds around. And what will happen is by saying this, what I've done is I've given them permission. I've given them permission to be okay, to be confused and to still be okay. And that's huge. Because the majority of the time, they're going to get confused and they're going to be like, oh no, I don't get this. I'm going to fail. I'm a horrible student. I'm stupid. This is over. I'm done. And I don't want them to do that. And so by saying, hey, by the way, this is confusing, and if you're confused, that's okay. It's amazing what a weight that takes off of their shoulders. It's amazing how much better results I get out of them in the long run by saying, hey, by the way, this is going to take you a couple of days, and be okay with that. Now, my bright kids get it literally as soon as it leaves my mouth, but the bulk of my kids, it's going to take a little while, and that's okay. All right, so really, for me, the strategies come out, or my tips and strategies come out in two places. One, how do we do the history? Because I think history is an important part of this. I don't have a whole lot of tips with the wave physics. Most state standards require that you talk about the wave physics at the beginning of this, like amplitude and frequency and wavelength and wave speed, and you get C equals wavelength time, the speed of light equals wavelength times the frequency, and using that equation. And we did equations a couple weeks ago in the Helping Students with Weak Math Skills workshop. If you haven't seen that one, you can go back and look at that and look at some of the strategies for doing equations, for doing the wave physics part. For me, I want to focus on more of the quantum mechanics. And so I think it is important to do history here. I think it's important to lay out the history of how we go from the Bohr model to the quantum mechanical model. For those of you who are not as familiar with quantum mechanics and what's going on here, so the Bohr model is what they should have learned in physical science and in middle school. This is the one where you've got the solid nucleus in the middle, and you've got rings of electrons going around the nucleus. And nice, pretty little rings. And the history of quantum mechanics basically is all about showing that, yeah, electrons don't go around in nice, pretty little rings. Nope, sorry. And so we need to get to that point. Now, I still teach the Bohr model. When I teach atomic theory, which is the chapter I do right before this, and then I do periodic table after this, for me, Bohr model is critically important because it may not be as technically correct as the quantum mechanical model. However, it's simpler. It's easier to use. It's easier to understand. And so it's great for when I'm talking about valence electrons. It's great when I'm talking about kind of bonding in a lot of ways that, I can kind of, reference a couple of things from the quantum mechanical model, like S&P electrons, but I'm really focused on, hey, valence electrons, I kind of think of those like a ring in a Bohr model. It makes it easier for the kids to understand. Like also when you're talking about periodic trends in the periodic table chapter, the Bohr model is still a useful model. And so I still teach it and I still use it. But we got to bridge the gap to the quantum mechanical model. And so for me, there's kind of a series of people that have to be talked about. And I generally try to talk about them in the simplest way possible. So first, you got Max Planck. I've always been taught Planck. Some people say Planck. And then the quanta, and the idea that we have discrete amounts of energy between energy levels. And you should be talking about line spectra and that kind of stuff here. Helping kids understand the idea of a quanta, that if you got an electron down here in level 1 and it's going to jump to level 2, the idea of a quantum is that it's not going to jump unless it has exactly that much energy or a little bit more. And kids are kind of like, well, what do you mean? Like, you mean if you put in like half the energy, it doesn't go halfway? I'm like, no, it won't go halfway. And I'm like, why? And I'm like, all right. So I'm like, usually the illustration I use is like, all right, y'all, imagine a plane flying from LA to Tokyo. And I give it half the gas it needs to get to Tokyo. Is it going to take off? No. I'm like, why not? Because it'll crash in the ocean. It won't make it. Exactly. Same thing with the electron. If it's not going to make it, it's not going to go. If it doesn't have enough energy, enough fuel to use the airplane model, it's not going to go. And I'm like, all right, well, what happens if you give a plane that needs to go from LA to Tokyo, let's say you give it an extra 10% fuel, what happens? It lands with an extra 10% fuel. It doesn't use it. In the same way, when an electron jumps from one energy level to the next, it uses or gives off, depending whether it's going up or down, it uses up a very specific amount of energy. And it's not going to use up more than it needs to. It's not going to use up that extra 10%. And so I use that as a really good illustration for them to understand what a quantum is, and how things are quantized. And that's where the name comes from, even though it doesn't come into play a whole lot later. All right, then we got to talk about Einstein and the photoelectric effect. Once again, I am assuming that you're at least somewhat familiar with this stuff because I'm going through it fairly quickly. Photoelectric effect. It's amazing that out of everything that Einstein is known for, he's not known for this for most people. But this is the one thing he actually got a Nobel Prize for. And so with the photoelectric effect, it's the idea, that he shines high energy blue light and electrons stream off. But if he shines red light, nothing happens. And he showed that even he could shine really, really dim blue light, and it would still have enough energy to emit electrons off the piece of metal. And he'd shine really, really bright, really intense red light, and it would do nothing. And so it goes back to Planck's equation that energy is related to frequency when it comes to light, and that the blue light had more energy and therefore is able to knock the electrons out, give them more than a quantum of energy, and make them get kicked out. And so this is a big deal up to that point. But then the really big deal is Einstein's the first one to propose wave-particle duality. And that's really the big thing that we have to emphasize when we're doing this, that Einstein's saying, all right, the way that the light is interacting with these electrons is not like a wave. Even though there have been so many studies and everything that's proven that light is a wave up to this point. And Einstein knew that. But he's like, all right, but in order to make my data make sense, the only way this makes sense is if light is acting like a particle. And he called those particles photons. And he said those photons were striking the electrons with enough energy to knock them out, kind of like a pool ball hitting another pool ball on a table and knocking it off the table. Okay, so something akin to that. And so he's like, all right, well, that's the only thing that makes sense. So I'm going to propose what is now known as wave-particle duality, that the electrons act like both a wave and a particle, which is just pretty mind-boggling when you think about it, that when we turn on a light, we're being bombarded by tiny little particles that are massless. And that's strange. And kids are like, okay, some of them are following, some of them are not. Main thing I need them to do is just hear it and learn it, and we'll kind of pull it all together at the end. Then you have de Broglie comes along. He says, well, wait a second. It's not just electrons. I mean, it's not just light. What electrons too? Electrons have wave-particle duality. And de Broglie then went on to say that, well, everything has wave-particle duality. It's just that most things, the wavelength is too ridiculously small to measure. And they're able to prove this, that an electron literally has a wavelength as it goes around the atom. And it's like, wait a second, is it a wave or a particle? Oh, wait, it's both. Okay, that's weird. All right, and then you just ratchet up the weirdness a little bit more by throwing in Heisenberg. And you make a comment, it's like, all right, guys, you can either know how fast the electron's going, its momentum, or you can know where it is. But you can't know both at the same time with certainty. The more you know the position, the less you know its velocity. And the more you know its velocity, the less you know where it is. And kids are like, huh? And then I'm like, this has been proven and it's true. And amazingly enough, it is one of the governing principles behind how stars age. That when a star collapses into a nova or a supernova is dependent upon Heisenberg's uncertainty principle. That basically, as the star gets smaller and smaller, the location gets more and more fixed. And so the uncertainty in the velocity keeps going up until we reach the speed of light. And then once it gets past the speed of light, the star collapses. It literally cannot maintain its own weight. And so uncertainty principle comes into this, and it's crazy, but it's true. And so this is where I usually pause and I say, all right, y'all, so we've got this Bohr model with pretty little rings. But we now have electrons acting like waves. So they're going like this around, instead of going around like this, they're going around like this around the atom. Then I'm like, oh, well, actually, to add further confusion, we have this. That we're not even actually 100% sure where the electrons are. So are they going around here? Or are they going around way out here? Or are they going around here? Are they doing something that looks like this? Like, what are they doing? And so I'm like, so at this point in time, the Bohr model falls apart. Primarily because of these two things. Because electrons are acting like waves, and we're not sure where they are. And so that's where I'm making this transition. I'm saying, hey, all right, guys, so all of these scientific things that were discovered in the early 1900s showed us that the Bohr model does not work. So we have to come up with a new model. And then along comes Erwin Schrödinger. For those of you who did not have the joys of taking physical chemistry in college, consider yourselves blessed. I took a quarter of physical chemistry 1 where I learned all about Schrödinger's equation and everything I never wanted to know about electrons. It was a horrible class. And it was just way confusing, very abstract, crazy stuff. But Schrödinger comes along and he proposes this quantum mechanical model. And it's based on probability. And so the way I generally explain this to my students is the way he does it is, right, I'm like, all right, if you were standing outside my classroom in the hall and you could not see through the window, and it was during a class period, you would not have any certainty of where I was in the classroom. Is that correct? They're like, yes. Right. But could you take a guess where I probably was? They're like, yeah. I'm like, all right, so it's the first part of the period when I usually do my teaching. Where would you think I would be? They're like, oh, up front at the desk. Up front at the board. And I'm like, exactly. That's where there's a high probability that that's where I would be. Now, am I definitely there? Could I be somewhere else? They're like, yeah, you could be at your desk. You could be walking around the room. You could be doing other things. I'm like, exactly. But there's a high probability that I'd be right there in front of the board. Like if this was my room, there's a high probability I'd be, up here by the board. Later in the classroom, when I tend to walk around and help them with their classwork, I'd be out here. And they're like, yes, exactly. And so I'm like, all right, well, that's what Schrödinger did with the quantum mechanical models. He said, all right, well, we don't know where they are exactly, but we do have an idea where they are 90% of the time. And so he creates this model based on probability. And that's where we get our energy levels and sublevels and orbitals and, your S, P, D, and Fs, all those crazy things. And so that's what he's doing. He's doing it based off of probability. And so this is kind of my first strategy is we've got to lay out just this bare minimum of, you got to kind of introduce this stuff because it's required. But really, it's these 3 that lay the foundation of going from the Bohr model to the quantum mechanical model. That electrons act like waves. We're not sure totally where they are. Therefore, we need to use probability to come up with a new model. And we get the quantum mechanical model. I make my kids memorize the shapes and all that kind of stuff, but that's not really my emphasis. All right, so that's confusing. And I can usually get through this in a day, day and a half. Now we need to work on actually doing electron configurations. And I do this very, very step by step. Because when you're trying to teach kids how to do electron configurations, you have your 3 rules. You have the Aufbau principle, Pauli's exclusion principle, and Hund's rule. And in abstraction, apart from seeing how they're being used, they're confusing. They don't make much sense. And so it's one of those things where I'm like, all right, guys, I'm going to put these things on the board, and I want you to copy them down, but I don't care if you understand them right now or not. I will explain them as we go along. And so I usually write, Aufbau principle. Electrons always fill the lowest available state first before moving on. Pauli's exclusion principle. Electrons always enter the orbitals in opposite spinning pairs. I'm getting my wording off because I'm doing this off the top of my head. Hund's rule, when filling in orbitals in the same sublevel, they will go in as singles before pairing up. So I'd have something like that written on the board. But then I would really focus on them more when we get here. So I'm going to start with some really simple examples, oxygen and manganese. So oxygen's here with 8 electrons, and manganese is here in the D block with 25. Okay. By this point, I've explained to them SPDF. I've explained to them that S has 1 orbital, P's have 3 orbitals, D's have 5 orbitals, and F's have 7 orbitals. And I've explained that each of them have 2 electrons. And so before I even start this, I introduce this concept of blocks. And I'm like, hey, all right, S has one orbital that can hold 2 electrons. Hey, look at this. It's two atoms wide. This is the s block. This corresponds to the s's that we're doing. All right, p has 3 orbitals. Each can hold 2 electrons. That's 6 electrons. Oh, that corresponds to this. 1, 2, 3, 4, 5, 6. Hey, this is my p block, with the exception of helium. It really goes over there. But for the sake of not having to recolor that, I just left it there. So that's my p block. And then here I have my d block because it's 10 across. And then my f block down here because it's 14 across. F block gets a little weird and I don't worry too much about it. All right, so I go through some examples. I give my kids the filling order diagram. Hopefully you've seen something that looks like this. That if you see, you list all of these in order, and then you draw diagonal arrows, it gives you the filling order. And I always do it in 2 colors like this just to help visually separate it for my kids. And I tell them when you get to the end of one arrow, you go to the beginning of the next arrow and you follow it down. All right, so I'm like, all right, let's start with oxygen, 1s. 1s can hold, has 1 line or 1 orbital. I'm like, all right, so orbital is a dash, and we label it 1s. And it can hold 2 electrons. So we put in our 2 electrons, and this is where I explain Pauli's exclusion principle. I'm like, hey guys, when we put these 2 in here, you're gonna draw 1 going up and 1 going down. That's just what that means. And then we go to 2s. Now we placed 4 out of the 8 electrons. And I'm like, all right, what comes after 2s? And they go, oh, 2p. I'm like, all right, good. So let's go 2p. How many dashes should it get? And they said 3. And I'm like, all right, great. So we do 3. And then I'm like, all right, guys, here's where this Hund's rule comes into play. And the illustration I usually use for this is if you've got a group of heterosexual men moving into an apartment. Let's say it's a 3-bedroom apartment. And you have to specify heterosexual, otherwise this illustration doesn't work. So you got, because kids will just take it all sorts of random crazy places. So you got a group of heterosexual men moving into an apartment. It's 3 bedrooms. First guy moves in. Hey, I'm going to take a bedroom. Second guy moves in. Is he going to join up with this guy or take an empty bedroom? He's going to take the empty bedroom. Same thing with the third guy. He's going to take the empty bedroom. And so my kids have learned to call this kind of the apartment rule. And that's kind of our little nickname that we have for it, that you got guys moving into an apartment. First guy takes the first empty bedroom, then the second empty bedroom, then the third empty bedroom. Only then when you add the fourth, do you start pairing up again. When you start pairing up at all. And so when we add the fourth, we finally pair up. We've now used all 8 electrons. We're done. And so I kind of introduce it this way, just simply counting electrons. It's slow, it's tedious, but it's the easiest way for them to get the grasp of it. So, and then I do manganese with its 25. And so we work through it again. We go 1s, and then we go to 2s, and we go to 2p, 3. And I'm like, all right, after 3p, what comes next? I'm like, is it 3D? They're like, no. And hopefully they should be seeing that it's not 3D. And they should see, oh, wait, no, the arrow goes here. I'm like, exactly. And I'll explain the energy level thing, that 4s is a little bit lower energy than 3D. But I'm just saying, all right, so this is what happens. It's got to go to 4s first. Then it goes to 3D. And so that kind of introduces this concept that we follow the filling order this way. And so once again, I'm just kind of getting them used to this idea of counting the electrons and doing that. All right, so that's my first step, just get them used to how this works with dashes and labeling and drawing arrows and all that kind of stuff. Second step is to what I call looking at the final electron and using the off-ball principle to make life easy. All right, so once again, we were looking at oxygen, which is right here. So if we zoom in on oxygen, it is in the second row, and I call them rows at this point in time because I haven't gotten to the periodic table yet. I haven't taught them groups and periods yet, so I'm going to refer to them as rows and columns, just because I haven't taught them groups and periods yet. All right, so I'm going to call this a row, and so I'm like, it's in the second row, it's in the P block, and let's count how far over it is. Here's the first one in the P block, second, third, fourth. It's the fourth one over in the P block. We would call that 2P4. It's in the second row, in the P block, fourth one over. So let's look at our structure again, what we drew. The last electron we drew was the fourth one in 2p. Ding, ding, ding. All right. And then I'm saying, well, so then I do it with manganese as well. I'm like, all right, let's look at manganese. Manganese in the fourth row. It's in the D block, and it's 1, 2, 3, 4, fifth one over. And I'm like, is this 4D? They're like, well, no, we didn't get to 4D. We went to 3D. So hopefully some observant kid notices. I'm like, exactly. When it comes to the D block, it's always going to be one less than the row number. And I make them write that down. And I'm like, F block's always going to be 2 less than the row number. So this is 3D5. Let's look at our configuration. The last electron we drew was in 3D, the fifth one. I'm like, all right, y'all, well, here's the deal. If you know where you end, everything else in front of it is already filled up because of the off-ball principle. Because the off-ball principle, and the way I usually explain the off-ball principle to the kids is that it's like building a house. That you got to finish the first, building a building or a skyscraper. You got to finish the first floor before you can build the second. And then after you build the second floor, then you can add the third. And then once you finish the third, you can add the fourth, and so on. And so we're up here on this floor in 3D. So all of this has to already be built. It already has to all be filled in. And so that makes it easy. I'm like, literally, you just draw your dashes and fill them all in until you get to 3D, and then you add 5. But that's where you're at. You're at your final electron location. And that's how I teach it. So like, for example, silver here is in the fifth row in the D block. So it's one less, it's 4D. And from the beginning of the D block, it is 9 over. So this is 4D9. And so I would draw or write everything up to 4D and fill them all in, and then simply go over 9, and that's what I would do here for the last one. And that's using off-balls principle to just make this a lot easier. All right, so once I teach them that, and so usually, let's see, if I'm teaching this at the beginning, so usually I can teach them this and this in a class period. And a lot of times I may stop there and let them practice this for a while without doing any writing of the configurations, or I add the third step, which is writing the configurations. I kind of go back and forth. So writing configurations is pretty simple. You just simply take your configurations that you have, and like, I'm like, all right, how many electrons are here? 2, 2, 4. So we write it like this. We use superscripts. 1s2, meaning there's 2 of them in 1s, 2s2, 2p4. Then I'm like, all right, let's look at manganese that we have. And once again, we can look at how many we have in each level and write them as superscripts. And then once again, here I bring in Hun's off-ball principle again. Sorry, it was a long night with a tornado warning at 4 in the morning. So I'm not talking super straight today. All right. So we have our final electron at 2p4. Everything else in front of it's full. We have our final electron at 3d5. Everything else in front of it is full. And so that's where I kind of remind them, all right, how many electrons can an S hold? 2. How many electrons can a P hold? 6. How many electrons can a D hold if you're going past that? And I'll kind of stop here and I'll leave it here and I'll let them do this for homework. The next day is when I add this. I do not want to add Noblegas configuration until I'm really certain that they're comfortable with doing it the other way first. I want them to be comfortable writing it all the way out like this and really kind of understanding why they're writing it out like this before I introduce this. I always do Noblegas configurations, even for my on-level, non-honors kids. I think it's something for them to, that's how they're going to see it in most chemistry books. Most chemistry books or most periodic tables, if you have the quantum, the electron configuration on it, it's going to be written in a Noblegas configuration. And so I really feel like it's something they need to see. And so I show them, hey, if we take this configuration, we look at all the way through the last full P, then we can look at that and, oh, that's the configuration for argon. And so we can then say, hey, this is argon, put it in brackets, and then put the rest of it there. And I'm like, so for something small like oxygen, this doesn't make a whole lot of sense. But for something really large like lead, that is a really annoying configuration to write out. It's really, really long. And so what I tell my kids is like, all right, go to the periodic table, find lead on your periodic table, go up one row and go to the end. And that's your starting point, that noble gas on the end, which for lead, if I remember correctly, yeah, xenon. So xenon's at the end of the 5th row. And so all of this is the configuration for xenon. And then you just kick on up after that. So xenon is 5p. And so we just start up after that on the filling order. And that's how we do noble gas configuration. And so I would go back to the filling order diagram. Sorry, let me go back here real quick. Yeah. So I would say, all right, where's xenon? Xenon's here at 5p. And then you just kick up after that. Kick up with 6s, then 4f, then 5d, and then finally get to 6p where lead is. And that's how we would go about doing that. So that really works well for those really big atoms that are just really too annoying to draw. And speaking of that, when I ask them to draw with dashes and arrows, I usually don't go 3D is about as far as I go. I may go to 4P, maybe. But anything bigger than that's just really hard to fit on a piece of paper, especially for kids who write bigger. And so I just don't go much bigger than that for drawing electronic configurations. Writing them, anything's fair game on the periodic table. And I'll, once again, just do about anything. But once again, kind of like I've talked about before, is I make sure my kids understand kind of what's going on with the configurations before I teach them kind of my final electron rule. And then I make sure they're comfortable with that before I teach them how to write the configurations. Then I make sure they're comfortable writing them before I teach them noble gas configurations. So make sure they master everything before you move on to that next step. All right. Okay, so Connie was asking a question of how do I deal with the transition metals that do not fill according to the chart? Not 100% sure what you mean by, you mean the ones where they kind of, the exceptions within the transition metals that can, like sometimes have like a, I think it's iron, can have 4s1 and then have like 3d something. Is that what you mean, Connie? Okay, so I say those exceptions for AP, or I save them for a Chem 2 class. I'm not trying to get them to master the nuances of quantum mechanics. I'm trying to get them to understand the basics of quantum mechanics. And the kids who are going to go on and learn later, they can learn the weird exceptions that transition metals do. And that's the same thing with intertransition metals, the F block. They can do some weird things with where those electrons go. And so I generally try not to worry too much about that. I'm just trying to get them to understand the basics. Yeah, so yeah, if somebody like points it out in the book and says, hey, but the book says this, I'm like, you'll learn about that later. Yeah, there's enough. I remember we didn't have AP chemistry in my high school, but we had Chem 2. And I remember sitting there with our Chem 2 teacher, and we would ask her a question, and she would pause before she answered. And at first, we thought it was because she didn't know the answer. And what we realized later was, oh, no. It's because she knew so much chemistry that she had to figure out how to explain it to us without confusing us. And I think for those of us who have a more of a chemistry background, if we get stuck on trying to be technically correct, we can confuse the stew out of our kids. I'm all about keep it simple, keep it where they can learn the basics. And then those who are going to go on to learn more chemistry, they can learn about the exceptions later. I just want to teach basic principles. So that's kind of my jet there. All right, quantum numbers. I only do this with an honors class, and only if I have time. If we're a little behind pacing of where I want to be, I'm going to skip this. Because once again, it's one of those things where I think it's good for them to know, but it's not critical for them to know as much as it is for them to know. If they can do SPD and F blocks and they can get the configurations written and drawn, I'm really happy with that. Because that'll help them when we get into bonding and they'll understand kind of what's going on. But quantum numbers are not critical. Once again, you're only looking at the final electron. So for example, oxygen is 2p4. If you're not familiar with quantum numbers, don't worry about it. But the first number is going to be this. The second number corresponds to p. And so in quantum numbers, so 2 is for the energy level. P has a sublevel number of, that's L. L is 1 for P. And then the third number tells you which orbital you're in. We're in this first orbital, and it's labeled -1. And we're spinning down, so it's -1/2. Once again, if you're not familiar with quantum numbers, I wouldn't worry about teaching it. It's one of those things that I don't really remember doing a whole lot with quantum numbers in college. I mean, I think I had it show up on a test once. It's just not that critical for them to know. But understanding basics of electron configurations is a lot more important. Same thing with manganese. The way, all right, let me see if I can try to explain quantum numbers in a way that's relatively simple. The first number is always the energy level. The second number corresponds to which sublevel you're in. So S would be 0, P is 1, D is 2, and F would be 3. Then the orbitals are numbered with 0 being in the middle. So this is -1, 0, 1. In a D, once again, 0 would be in the middle. So this is -1, this is -2, this is +1, this is +2. All right, so that's kind of how I try to teach it to my kids. Like the 0 is always in the center, and then you go this way negative, go this way positive. And then so that's what this number corresponds to. And it's the one where you put your last electron. So here, that last electron I drew with this one going down. So this is 0, this is -1. And then down here, I drew it in this one, which is +2. So 0, 1, 2, that's where this one is. And if it's spinning up, it's a +1/2. If it's spinning down, it's a -1/2. That's the real quick gist of quantum numbers. And once again, it's not something I worry about a whole lot. I have probably taught it 5, 6 times in my 15 years of teaching. Like it's not something that I've stressed over. If I've got the time and I've got a really bright group and I want to kind of push them a little bit, I'll throw this in there. Because it's great for bright kids. Because it makes them think in a little bit different way. They're looking at it differently. It makes them learn in a different way. So for your really bright kids, especially if you've got them somewhat segmented, you've got like your really bright class and you've got kind of more your more average class, push your bright class with this. Like challenge them with quantum numbers. It's a good way to kind of challenge them and push them one more level. But if you've got a class that's mixed, where you got like some of your brightest kids and some of your weakest kids all together in the same class, I'm probably not going here. Because my weaker kids are probably doing great to be doing everything else. That goes back also to what I do with Noblegas configuration. Noblegas configuration is great, but I don't require it. Once again, maybe for honors kids, I would require it. But for my average kids, I'm like, hey guys, if you just want to write it out like this, and that makes more sense to you, go for it. If this makes more sense to you and you like how it saves you time, go for it. But as long as you give me the right answer, I'm okay with it. Like I said, so like with honors, I'd push them. I'd push them and say, no, you got to use this. Everything has to be written in Noblegas configuration because that's how it's going to be written later, and I'm just going to push them on that. But for my average kids, I'm kind of like, y'all, whatever you're comfortable with, get me the right answer. If you want to write it all out, and usually on a test, it'll be half and half. I'll have probably half my kids that write it out like this, and it's usually going to be my weaker kids because they just want to be able to follow that filling diagram, and they don't want to have to think about an extra step. They just want that. They just want to follow those arrows on that filling diagram and get done. And speaking of that, I've kind of gone back and forth once again, depending on the year and depending on the strength of my students, whether or not I give them the filling diagram. Most of the time, I will teach them how to draw it themselves, and then expect them to do that. And so, like when my kids get their periodic table at the beginning of the test, they'll flip their periodic table over, and on the back they'll do the filling diagram real quick. Just something like that, just to try to help them remember how to do it. But once again, my weaker kids, they would rather just follow the filling diagram and not have to stress about, trying to figure out Noblegas configuration. And if I've got really, really weak kids, I may give them a copy of the filling diagram just for the sake of, all right, y'all, I don't really care if you memorize this. I just need you to be able to pull this off. If you can use it, we're doing good at this point. But once again, I kind of vary my expectations based on the strength of my students. But I do kind of have my bare minimum that I request of them to be able to do. Like I said, quantum numbers is that way. So for me, once again, with quantum mechanics, it's give your kids permission to be confused. Give them space to understand that this is abstract, this is weird, this is hard, and say it's okay to be confused for a little bit. And I think that frees them up to not stress themselves out. Because we've all had those students who freak out when they don't know what's going on. Okay. And then with history, I try to keep the history relatively simple. Quantum history is one of those things that you can get really bogged down into the details, into the weeds, especially with Max Planck and line spectra. And, I do a flame test real quick with them and let them use prisms and see the lines. And, that's really cool. But I really try not to get bogged down in the history. I try to kind of really hit the high points, but make that connection between Bohr and quantum mechanical, make that bridge for them of showing why we had to get rid of the Bohr model, because of wave particle duality and uncertainty, and that we moved to this new model that's based on probability. And then I focus on this. And I really love showing my kids how it's connected to the periodic table. And that's why I focus so much on that idea of finding the final electron. S, P, D, and F blocks on the periodic table, where the rows fit in with what they're seeing as their sublevels. 3D is in the fourth row and 3P is in the third row. And I want them to see all those things because that's one of the amazing validations for the structure of the periodic table is that it fits this model so well. And I want them to see that connection because it'll help when we get to the periodic table, because I do periodic table as my next unit right after this. And so I find it really helpful for them to have a good understanding of this going into that. Because it'll also help when we get to, groups. Why do groups have similar properties? Because of, when I can say, hey, oxygen's 2p4, sulfur is 3p4, selenium is 4p4, tellurium is 5p4. Do we see a repeating pattern here? Yeah, they're all p4s. And then that can help them see those trends in the periodic table and understand why. Well, it's because their electron configurations look the same. That if we look at the end of their electron configuration, they're all going to look like this. Whether there's a 2, a 3, a 4, or a 5 here, they're all going to have the same look at the very, very end. And that's helpful going in the periodic table. All right, and then, like I said, just doing the actual drawing and writing. I do drawing first, and then I do the writing, the 1s2, 2s2, 2p6. And I think it's really important that we're introducing or really emphasizing the rules, off-ball principle, Pauli exclusion principle, and Hund's rule as we go through this. And I really try to teach them, even if I'm doing, like if I was writing this out on the board, I would draw it using Hund's rule. So like when I got here, I would go, instead of going up, down, up, down, up, down, I would go up, 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 down, 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 just like I would with Hund's rule. Then up, 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 down, down, down. So I'm drawing all my ups before I draw my downs, just once again, trying to illustrate and demonstrate and be consistent with what I'm doing. So I don't cover trend. I cover trends when I get into the periodic table unit, yes, but I keep it really. I explain it, but then all I want them to memorize, like I want them to understand the science behind it a little bit. But then what I expect them. So Connie's asking, do I cover trends much? Atomic radii, electronegativity, et cetera, for regular chem. And what I do is I make it so that I want them to memorize that everything is, let me get this straight in my head real quick. So ionic size is down and to the left. Atomic and ionic size is down to the left. So if you're looking at a periodic table, let me go back to find a slide that's got a periodic table on it real quick. Yeah. All right. So atomic size and ionic size always go down and to the left. And then everything else is up and to the right. So effective nuclear charge is to the right and up. Ionization energy is to the right and up. Electron affinity is to the right and up. Electronegativity is to the right and up. And so I just make them memorize that atomic size and ionic size are down and left. Everything else is up and right. And then once again, I don't worry about all the exceptions and the bumps and the trends, and then I always make them compare things that are left and up and down from each other. So I would always like sodium versus sulfur, or sulfur versus tellurium, like so that they're in line with each other. I would never do tellurium versus aluminum because that goes against the trend. Well, the trend is up and to the right. Well, that's up and to the left. Like, what is that? That's confusing. And so I would never test them that way because I find that confusing. And so, but yeah, I could do indium and sulfur and like up and right. Oh, sulfur's the higher electronegativity or the higher ionization energy or the higher electron affinity. And that's what I do with trends when I get in the periodic table. All right. Run back through this again. Kind of going back and forth today. All right. So once again, grading. I am a huge proponent of partial credit. I've said this in some of the other workshops. If it weren't for partial credit, there'd be more than a few tests in college that I would have gotten zeros on. Georgia Tech is all about partial credit. It's the only way you pass anything. And so for me, I'm focused on the final electron and the filling order. And kind of as I've talked about before, my grading changes as we go along. So when I'm first teaching them to draw the configurations, I may count 1s as a point, and 2s as a point, and 2p as a point, and kind of do it that way. Or I may just, and so I vary it a little bit, but I try to break it up into sections or parts. But this is pretty much what I focus on, that pretty much any configuration is always going to be at least 2 points. Did you tell me where the final one is? And did you get everything else in front of it right? Just doing the off-ball principle and filling in everything in the right order. And that's my general principle for grading these. Like I said early on, I may give them a little extra grace with some points and expanding it out into steps a little bit more. All right. So I've used this before, and it's been really cool to kind of hear comments from people like, hey, I'm in this stage or I'm in this stage. And this is really, once again, how you grow. So, you're not going to be here because you're at these workshops. You're trying to grow. So you can either grow in content, trying to learn stuff, and that's where you are. This is probably a hard workshop to listen to because quantum mechanics is difficult. And if you're not already comfortable with that content, it's really difficult to teach. And so you've got to learn the content first. And you've got to learn the quantum mechanics first. And then once you understand it, then you can grow and like, how do I actually break this down and communicate it to my students? And then once you get that down, then you can start being creative and bring in, all right, how do I take the flame test and make it a cool, safe thing for the kids to work with and that kind of stuff? And how do I branch onto that? Speaking of the flame test, that's one of the tests, that's one of the labs where, or demo where I've heard horror stories of kids getting injured. And next week, I'm going to be talking about lab safety. So that's just kind of my plug for next week. I'm going to be talking about lab safety and how to do labs and demos well, and how to take care of not only your kids' safety, but your own. Because a lot of chemistry teachers miss out on their own safety along the way. And I've also talked about this stuff. So I've got the rest of the workshop series. Like I said, I've got lab safety next week, and then we're doing reactions after that, and then moles and stoichiometry. I'm probably looking at changing out the last workshop that I'm giving. I think I've got it like the path for chemistry success or something. I know there's a lot of teachers who are teaching at private Christian schools that I've just seen from the comments, and that's part of my past. And so I'm probably going to do something about how do we teaching science in a Christian school, and how do we make faith and science interact with each other. And that'll probably be the last workshop I do. And then I've got my other products. I've got my crash course that's designed to help people with teaching the content, knowing the content. And then the academy that focuses on the teaching communication aspect of it. But what I'm offering is my desire for you is for you to walk into a classroom being fully confident and fully prepared. That's what I want. I want you to be able to walk into a classroom and not know you know your stuff. And that's my desire for like the crash course. And then for like the academy is to, like, not only to know your stuff, but have everything you need. And know you have everything you need to communicate it well. And so I want to try to give you that confidence and that preparedness that, I don't know, there's just something about a lesson when you know it and you know you're prepared, a lesson just comes off better. Your kids get it better when they know you have that confidence. And that's what I want to offer with these things. And in both of these things, I'm offering something that isn't offered anywhere else to my knowledge. Is with the crash course, I'm offering you one-on-one teaching with me. That's what my office hours are. You show up during an office hour, it's going to be a Zoom call, kind of like this. I can bring your screen up. And I can replace this with a sticky pad, and we can work on problems. And you can show me where you're struggling, and I can show you, and we can work one-on-one. Or like if I've got 3 people during office hours, we can work 3-on-1, and we can work through it very much as a teacher for you. Because one of the hard things about being a chemistry teacher is most of us are the only ones in our school. Or we have somebody else who's like really super smart in chemistry, and they leave us kind of behind. Same thing with the academy is I want to be your mentor teacher. Over this last year, I've answered questions about dealing with administrators, dealing with parents. What do you do when kids whine about homework? We've covered like how to prepare kids for exams, how to prepare kids for a chemistry exams different, I feel like, in some ways than some other exams. And so we've covered a lot of these different things, not just the handouts and the content, but just how do you teach? And I want to be your mentor teacher. I want to be that person who's there for you. And that's what I'm offering with these things. But I'm also offering you time. I'm trying to save you time. Yeah, the crash course, it's almost $300 as it is. But over a course of 36 weeks, if that's less than $10 a week, and I guarantee you I save you more than a couple hours a week of studying the content by yourself at home. Staying up late, trying to make sure you understand it before you walk into the classroom the next day. And that's what I'm trying to do with the crash course. Same thing with the academy. It comes out to a little over $1 a day. I think it's $1.25. But once again, I'm trying to save you just time. Giving you the resource. You don't have to make your own handouts. You don't have to make your own tests. You don't have to make your own review sheet. It's all there for you. And then if you run into problems, you can ask me. And that's what I'm trying to accomplish there with those things. That I want to give you not just stuff, but I want to be with you through it. Just kind of like I'm trying to encourage y'all to do with your students, that it's not about giving your students information. It's about being with them through the learning process. And that's what I want to be to you. I want to be with you through the learning process of, whether that's the crash course or the academy, wherever you happen to be. If you're growing in content and that's where you need to focus this year, then the crash course is the place for you. Really spend this year focusing on the content. Communication will come later, and be gracious with yourself and knowing that communication will come later. If you're really comfortable with the content and you want to work on, what I call kind of the double bell curve, that we got our brightest kids get it, and then everybody else is kind of down here and they don't get it. Bridging that gap, bringing everybody together into a single kind of normal grade distribution. That's kind of my goal for everybody, to be able to kind of bring that group that gets kind of left behind and bring them up with your bright kids and bring them together as one single group. That's what I want to do for you. And so, those things are there. I've got more information at the website, teachinghighschoolchem.com. It will give you a list of what each one of those has. You can learn a lot more about them. If you want to look at the sample of what the academy stuff looks like, it's here. If you looked at it earlier in the summer, I've just redone it, how I'm going to have it arranged now. In the future, I'm kind of revamping how I've got it arranged to try to make it a little more user-friendly. So with that, it's been fun being with y'all, and I look forward to seeing y'all next week.